Welcome to Data Brew by Databricks with Denny and Brooke. This series allows us to explore various topics in the data and AI community, and whether we're talking about data engineering or data science, we interview subject matter experts to dive deeper into these topics while enjoying our morning brew. My name is Denny Lee. I'm a principal developer advocate here at Databricks and one half of Data Brew.
And hello, my name is Brooke Wenig. I'm the director of our machine learning practice and the other half of Data Brew. And today I'm thrilled to introduce Shashank Rajput, who is a research scientist at Mosaic and Databricks. Welcome, Shashank. How did you get into the space of LLMs? I know you have a very academic background, so perhaps we could start there before we dive into the main topic of today, which is all about mixed attention.
Sure. So before joining Databricks, I was a graduate student at UW-Madison. And for the most part of my PhD, I actually worked on theoretical and mathematical aspects of the foundational machine learning and optimization. But then I think when ChatGPT came out, everyone got really excited. And I looked at it and I was like, damn, I'm really interested and I'd like to see how it really works. So then I started understanding the theoretical aspects of how it works and mathematically understanding how powerful the transformer architecture really is. The transformer architecture is what powers all these LLMs. So then we discovered it's powerful enough to actually simulate a full-blown computer. So then I got more and more interested, and then I did an internship at DeepMind, and there I further worked on transformer. We used transformer to build one of the first generative recommender systems. So applying the generative AI technology to recommender systems. And then so I was interested in this, and then I joined Databricks, their pre-training LLM team. And then I've been learning ever since. And that's how I got started in the LLM field.
Awesome. Yeah, I just went through the State of AI report, which showed 74% of all of the LLM-based paradigms still using transformers. So I know there's a few alternative proposals out there, but that one's definitely the main one. And speaking of transformers, from the original paper, attention is all you need. Before we get into what is mixed attention, perhaps we could just level set to make sure everybody understands what is attention.
So if you think about, let's just take LLMs which take as input text, and let's just say that they take one word, each token is a word, whereas technically tokens can be different than words. But let's just assume that LLM sees a sequence of words, and the way LLMs process each word is there's a feed-forward part, which is the part of the network that just looks at that particular token essentially. And then there's the attention part, which only looks at the other token. So it's you can think of it as a grid. FFNs, the feed-forward networks process each token. If this is your sequence, then FFNs process each token individually, and then attention looks at all the other tokens in your sequence. Well, it also looks at yourself, but it also looks at every other token in the sequence. And then the way it does that is it essentially creates, for each other word in your sequence, it creates something called a key and a value vector. And then for the current token that it's processing, it computes something called a query vector. So it's hey, I have this word, and this is the semantic embedding, which is a query vector for this word. And I would like to query all the other words in my sequence to see which one aligns the most with this query. So whose key vector aligns the most, and that's how it tries to judge the importance of any other word in your sequence. So if, let's say, you're processing a particular token and you're basically trying to output the next token, and then you see which other, in the simplest words, which other token is the most important for the current context. So that it does using attention and using these key, query, and value vectors.
And so quick question with that. So this is more of a newbie question. When you say sequence, when it comes to applying the token, Is the sequence in this case a sentence, or is it a phrase, an entire paragraph? I'm curious as in how that feed forward or that attention is applied.
Yeah, it can be as big as you want. It could be just a sentence, a paragraph. So when people say that, there's this new model which supports 100,000 context length or 1 million or 2 million context length, it's essentially that you can feed all that like 1 million words into the transformer, and it will look at all of those.
Okay, gotcha. Well, then I guess that naturally makes me want to ask the question, what's the drawback of standard attention? Like, that seems like a grandiose solution that solves everything, but obviously there's some drawbacks. So why don't you tell us a little bit about that in that case?
Right. So there's the main drawback is so it's kind of like a pro and a con. The thing is, attention looks at every other word in your context, right? So it has the capacity to like at one go look at everything, right? So that's a good thing. But also that's a bad thing because it's spending too much time and memory looking at every other word. Whereas most of the time, right, if let's say you've asked the LLM to write a long novel or something like that. So it's, let's say, at the millionth token. You don't really want to look at all the other tokens like necessarily. Most of the times, your next word that you're trying to output can just be derived from the past 100 or 200 words. Like, even if you're writing a novel, right? And you're like, let's say you were writing Harry Potter, and Harry Potter switched his, and then the next word would probably be wand. You don't need to look at like all the previous Harry Potter like tokens to know that like the next word is probably going to be the wand, right? So yeah, that's how. So basically, one the advantage is that it can look at everything. The disadvantage is that looking at everything is computationally expensive and also takes memory. And this is both during training and inference.
Got it. So then, based off of that context, I guess this leads on to talk about this idea of mixed attention, right? So what exactly is mixed attention? I believe it's experimental, but please clarify.
Yeah. So as I said, right, the attention mechanism looks at all the other tokens, all previous tokens in your context, but it doesn't really need to always. In particular, this attention mechanism is present in every layer of your transformer. So if your transformer has 100 layers, each layer will have this attention. And so there have been works which there have been works which show that even something like a sliding window attention works pretty well, which basically means instead of looking at all the other tokens, you're only looking at, like, say, the last 100 tokens or last 200 or last 1,000 tokens instead of looking at all the. So that's why it's called sliding window attention, because your attention window literally is just like sliding as you keep outputting more, it keeps sliding. So you're always looking at the last 100,000 tokens. And that saves a lot of memory during inference, and it's also faster. But this mechanism did lead to like some degradation in model quality. In particular, as you can see that if you're only allowed to look at the past 1,000 tokens, you won't be able to answer, let's say, a question which occurred like 1 million tokens ago. And there's like, even theoretically, you can show that like with the sliding window, the maximum context length theoretically possible is your sliding window size times your number of layers. So if you have a 10-layer network and your sliding window is 1,000 tokens, the maximum theoretical token that you can attend to in the past is 1,000 times 10, which is 10,000. But in practice, it's much lesser than that. But what we saw was, if you add just a few full attention layers, right? Let's say you have 10 layers in your model, and you have just 2 full attention layers, and the rest are all sliding window. We saw that you were able to recover a lot of your accuracy, a lot of your model quality on longer contexts. So that's one thing. And the other thing which we were looking at was this concept of KV cache sharing, where there have been some papers which what they did was, so you remember I told you about like each word has its query embedding, and it tries to match it with like the other tokens using their K, like key embeddings, and then they also use the value embeddings. So during inference, what happens is these key and value embeddings are essentially the representation of all the other tokens. That's what you store as your context. And so you really want to minimize that. So people found that if you share the KV cache, KV representation across layers, so like not each layer has its own key and value, that if you do that, you still have you're still able to get good accuracy and like good model quality. So we were playing around with not just this, but also some other ideas like adding Mamba layers in the middle, which is like a completely different form of, well, it's not even attention. It's like a different way of, processing sequences. So we were playing around with these, and that's when a blog by Character AI came out, which was also exploring the exact same ideas of mixing these up. But they said that they had productionized it, and they were like serving huge QPS with those models. So we were like, we knew that this is gonna work because some other people have already productionized that model. So like whatever we are exploring is valid. So that gave us a boost, and we were already trying out some different configurations, but then we decided to choose just the ones that they had like talked about a little bit. But then what they were doing was they were using both sliding window attentions, interspersed with full attention layers, but then also sharing KV cache, which is also something that we were trying, but they had a particular configuration that they had shared. So we started off with that then. And we saw that just using that naively actually did not give us good results. So we started playing around with changing the configuration, and then we found that, okay, changing the configuration even a little bit like makes the model quality change drastically. So we were like, okay, let's just study this. How should we arrange the sliding window layers? What should be the sharing pattern and all that stuff?
So thank you for all that context. It really seems like this is all just a question of trade-offs. Of full attention is great, but it's going to be costly, both training and inference, as well as potentially unnecessary. And so with mixed attention, it seems like you kind of get the best of both worlds of you can get improved performance without necessarily sacrificing too much on qualities. Is that a decent synopsis?
Yeah. So that's what our experiments showed. We saw some degradation on some metrics, but we weren't sure if that was because we just didn't train them enough, or there exists some other configuration which will be able to recover that quality. But like for most of the other metrics and like metrics that we care about, like the quality metrics that we care about, we were able to retain the same quality.
And before we dive into like the metrics and how you evaluated it, I'm just curious, is there a differences in the network itself, whether you have the full attention at the beginning, at the end? Does it really matter where that happens in the network?
Yeah, that's a great question. And that's actually one of the things that we explored in the paper. We found that having a full attention in the very first layer actually did not help at all. So which was surprising because I always assumed that in the very first layer, if you like if in the very beginning of processing, if you're able to look at every other thing, every other word in your context, it would be helpful. But turns out it's not. And then the way I mentally justified that was, hey, like initially you only want to look at the local context, and then you figure out what you really want from your longer context. But I don't know if that's how it's really happening. But yeah, having the full attention layer in the beginning does not help, at least in our experiments. But having it in like third or fourth or fifth layer helps a lot. So, and like also like having, we didn't experiment with having a full attention layer only in the last layer, like all the other are sliding window and only the last layer is full attention. So I'm not sure how that would work out. But that would be a great thing to try.
It's really interesting. Before I definitely want to understand a little bit about how those models value, but what I find really interesting about it, especially when you're talking about sliding windows and caching, is that you're literally reminding me of like the L1, L2, L3 like GPU or CPU caches. And I'm wondering, in some ways, if the mixed attention is analogous to that, where you basically, some cases you're going to use sliding windows, just like in some cases you use the L2 cache, which is embedded with the chip itself, versus the L3 cache, which is like around the whole system, which is analogous to full attention. So I'm just, I don't know, I was just thinking, happened to be thinking about that way when you were talking about it. That's all.
Yeah, I mean, there are some analogies there because like sliding window is faster. It's gonna be faster.
Okay.
But if you really need longer context, then you need a full attention. But I think in L1, L2, L3 cache system, it's like if you have a cache miss, you go to a higher level.
Right.
Here in sliding window, there's no such concept. Like if you don't, it's not like it's dynamic window size that you run attention and then you find out, okay, I'm missing something, and then you increase the sliding window length and then you try again. But like after a few layers, if you have a full sliding window, full attention layer, that's when you can you'll be able to look. Yeah.
Gotcha. So in that sense, not the L1, not a hop from L2 to L3 is just more a matter. Just keep using the sliding windows, and then you're fine, because later on in one of the layers you'll have the full attention anyway, so you're good to go. You'll end up getting hit then. Okay, got it.
Yeah.
Okay, so this naturally leads me to ask the question: how do you even evaluate all these models? Like, what's the mechanism by which you understand what's effective, what's not effective? When you build the architecture, how many layers you want to build in? Like, how is this evaluated?
Yeah, so when you design the architecture, so we in our team had like this different size of model architecture. I think like some are pretty standard. We had like an MOE architecture which we had pre-decided. It was more of a trade-off between like, the bigger the model, the more GPUs it will need for training, and also the more inference, like the more time and computation it needs for inference. So for example, for these particular experiments, I knew, let's say I would have a budget of like X GPUs, and I want to run so many experiments. So what's the size of the model which I can viably like train in those, like this much computational budget? So that's how essentially we decided the model size for these experiments. But like to evaluate the quality, we have multiple metrics. The first thing you look at is just the loss, how it goes down. If your model architecture's loss is, if like say you're comparing two models, model A and B, and rest every other thing is the same, like they're trained on the same data, they're trained on the same like type of data, everything. Like if the data set is the same and you have trained that for the same amount of time, then if one of them has higher loss than the other, then probably that's a worse model. So that's the first thing you look at. But most of the times, so that thing does not work super well for long context models, because in the end, loss is just like predicting the next word. Most of like the loss, the way you compute is, you give it a data set and you try to train on it by asking it to predict the next verb, and you compute the loss on it. And for the bulk of the training, you're training it on just like normal internet data. And as I said, most of the times you don't really need to know the entire context to predict the next word, right? So then you need to have evals, one like evaluation data sets or evaluation metrics. So you have some like long context evals that exist out there. So you have the existing like short context evals, which are like the ones that people talk about, MMLU, Swag, and all these. But since my focus was on long context abilities, we were looking at long context evals. So one of the first evals that was proposed long ago was quite interesting. It's like you have this huge piece of text and you hide a key there somewhere, or a needle. And the task is called needle in a haystack. So you hide some particular text in there, and then at the end you ask the model, hey, what was the text I hid in this context? So if, like it's a million length, or like 100,000 length text, and you somewhere in there hid like a little word, and you're asking the model to retrieve it. So that was one of the first evals that was proposed for long context. But now there are even more evals. For these experiments, we chose a particular eval like set, which is called ruler, where they do this needle in a haystack, but they also have some other um, interesting evals where, let's say, one of the evals is the question answer eval, where what you do is you take paragraph from, let's say, Wikipedia. Let's say you take like 100 Wikipedia articles, you concatenate them, and then you ask a question about any one particular document in the middle. So the model has to look at the question, figure out which particular of all these 100 documents, which particular document that contains a relevant answer, and then it has to go there and figure out the answer. So this is kind of similar to what would happen if you have like retrieval augmented generation, where you have a bunch of documents and then you're asking the LLM to do something about that. So yeah, these are the kinds of evals that we are used mainly.
Yeah, the needle in the haystack one is a fun one. I remember, I think it was when Claude first came out, people asking, like putting a random fact in there, like about a squirrel or something,
Yeah.
and it would reply back with, "Here is the answer," but it feels like you're intentionally doing this to try to trick me.
Yeah.
It's like the models are definitely being trained. I guess question for you, are more and more models being trained with needle in a haystack like evaluations?
It's so for closed labs, I don't really know. Like, I don't know what OpenAI or like Anthropic is doing. But it seems like for the open source models and the models that we are training, we're not explicitly training on needle in a haystack. In fact, one big part of what we're trying to do is we're trying to figure out what evals are really important, let's say for our customers or for the public, because needle in a haystack, it was one of the preliminary evals, but it's not really very useful, right? Like, if you really want to search for something in a huge piece of text, just search it using grep or whatever, like some other computer functionality. Transformers are probably like really expensive way of doing that, and also error prone. So one really important direction of research, or like, is just figuring out what kind of evals do people care about.
They do.
And then once you have the eval, you can think about how you can train a model to be good at that task. Yeah. So, for example, for long context, one problem is that you don't really have a lot of high quality long context data. So people resort to using synthetic training data sets. So for example, for these experiments, what we did was we did the same thing. We took Wikipedia articles, concatenated them, and then asked questions about the articles and then trained it on the answers. So this sort of thing can be done using, so you can take an existing LLM, give it one particular Wikipedia article, ask it a question about it, right? And it'll create a question and an answer. And then what you do is you concatenate all the hundreds of Wikipedia articles together. And then at the end, so give an LLM all of these and then ask it to answer the questions that the other LLM generated. So basically, you can use an LLM which has a shorter context to generate questions and answers, and then synthetically just pair it with a bunch of other Wikipedia articles, and then train it on answering that question.
Very interesting.
Yeah, there are other ways of doing that, doing synthetic long context data generation. One is like just summarization. If you take a huge text and just create a summary. So the way you create a summary is you first chunk that long article up and then feed the individual smaller chunks to an LLM and ask it to summarize those, and then feed all that summary into another LLM to summarize it again, and you keep repeating it until you have a small enough summary, and then you train a model on the entire context to generate that small summary. So yeah, there are various ways of doing synthetic long.
I'm just curious, like you just said you use another model. I'm just curious, does it actually have, like, can you just use the same model to summarize but with different prompts, or are you actually literally using a different model just so that way you have different contexts Okay, I just probably overloaded the term context right now, by the way. So my apologies.
No, so you can do it either way. The
Okay.
thing is, okay, so there would be advantages of using the same model, and there would be advantages of using a different model. The advantage of using the same model is that there wouldn't be a huge distribution shift in your generated output. So the LLM wouldn't be confused by the the LLM would focus on just the gaining long context abilities essentially, instead of like trying to learn all the distribution shift. Because let's say model A is being trained by you, and you're using model B, which was trained by another company, and model B starts off its output with some interesting whatever style. Your model will end up starting to learn that style instead of what you really wanted to learn, okay? Which is long context abilities. So that's one. But like in the other, where it might be useful to use a different model is this, that other model is really, really good quality, right? Let's say you're training a smaller, you're training a smaller model, let's say Llama 8V. Like, I think that's what they did in for Llama. Actually, for Llama, they trained it with 8V outputs. But let's say you have a way of generating high quality answers, but that answers come from a different LLM. Then you'll use that because that's higher quality. But if this could also be another case where the higher quality model is really slow to generate outputs. So in that case, you might compromise and say, okay, we'll use a faster model which does not have as much speed. So yeah, there are all these factors. So like, yeah, you might really try to figure out which one works best for you.
So I have a lot of follow-up questions for you just from that. First one is about the distribution shift.
Yeah.
Would you see that if you were to use like the Llama models, but different sizes? Because they were presumably trained on relatively similar data. So I'm curious if you would expect to see that distribution shift within the Llama family, just different sizes versus like the Llama versus any of the proprietary models.
Yeah, within the Llama family, you probably wouldn't see. In fact, there isn't much distribution shift that's intentional. The way they did was not only they trained it on similar data, but also the smaller model were distilled on the larger model's outputs. So when you distill, you're really enforcing that not only the output, but like before the output, distribution of the, so like LLMs don't really just output a token, they output like essentially like a probability over what the next token could be. So you're forcing it to match that probability. If you're when you say distilling, most of the times it just means you're trying to match the probability distribution. So they intentionally like distillation has other benefits as well, but one of the benefits is that you also match the distribution, output distribution, and this really comes into this really becomes helpful in other places as well. Like if you're doing speculative decoding and stuff, where you have a larger model which is verifying your outputs, but a smaller model which is like actually generating the outputs. So in that case, if their distributions are different, then the larger model might say, "Hey, this is wrong output," whereas the output could be right. It's just saying in a different way, or essentially doing that. So having a family of models which have similar distributions is really helpful, and like you might train them that way, like to ensure that.
That totally makes sense, and thank you for the additional context. Danny, I did the same thing as you, overloading the word context. I have to remove that word from my I don't even want to say the word vocabulary.
Even now we're gonna overload vocab at this point. Yes, exactly.
So in terms of using an LLM to generate question-answer pairs based off of documents, I know one of the drawbacks is you won't be able to generate a question-answer pair where it's like, I don't have the information to be able to answer this question. Because if you're generating it from the document, therefore you would have the answer, presumably. And so I'm curious, when you're training models, how do you avoid that problem?
Right. So that's a very interesting question. In fact, that's something that I haven't done in my experiments yet, but like I really want to do next. I don't have much context on how people do that, but I'm pretty sure people do that because there are evaluation benchmarks which do exactly that. That they provide a paragraph and then ask a question which you can't answer it based on the context, right? And so then the LLM's task is to say that, hey, I don't have enough information from the context to answer this, instead of just hallucinating something. So there are evaluation metrics and benchmarks out there. I like, so because like we're working on follow-up of mixed attention. So I really want to like train on that kind of data where, it's trained to answer, hey, I don't have enough information to answer this. But unfortunately, that's the extent of my knowledge. I am guessing one way to do that would be generate questions from a different document and then provide it a different document from a different source. So for example, generate a document, the question from the document about Milky Way, and then ask it a question about Andromeda galaxy or some other galaxy. And yeah.
Or the chocolate bar.
Yeah. Oh yeah, that could be a really interesting thing as well, because if you ask it a question about Milky Way, but the is there a chocolate bar called Milky Way? Right.
Yeah, that's right. Yeah, there's a chocolate bar called Milky Way. That's why I brought that up.
Yeah. Because for some reason I remember there was one chocolate named named after galaxy. I didn't remember it was Milky Way or Andromeda. But yeah, Milky Way would probably make more sense if it's a milk chocolate, right? Oh no, actually Milky. Yeah, I remember eating Milky Way. I have such a bad memory. I actually
it's
have
okay.
eaten.
We're throwing the context all through the roof. Oh, I'm sorry for that one. I'm sorry for that joke.
Yeah, but yeah, if you give it a Wikipedia article about, let's say, Milky Way, the galaxy, and ask it question about Milky Way, the chocolate, that would be a good training example, because you should train it that even though these look similar, the article is about a different Milky Way. Yeah.
So I hope it don't mind, but you brought this up with the mixed attention a little bit earlier. You brought up Mamba architecture, and I've heard about it, but I don't know enough to be able to explain it. So, this is definitely, can you explain like I'm five? Like, what exactly is the Mamba architecture here?
So, so before Mamba architecture, Mamba architecture is basically belongs to the family of machines called state space machines, where essentially, okay, so if let's consider transformers, when you're outputting the next word, you do have essentially a state, which is your KV cache, which is your context, like the way your context is stored. And the problem with transformers is that the benefit and like drawback of transformers is, as we discussed, that this context, as it grows, your memory requirement and computation grows, because in particular, the memory grows because your KV cache, which is like your internal representation of your context, has a vector for each word in your sequence. So if you have 1,000,000 words in your sequence, your KV cache would be proportionately long. So it will be like 1,000,000 tokens long. So you do have essentially a state, but the state grows linearly with the input. But like the other states, like not the other, but like the state space machines like Mamba, and actually even RNNs and like LSTMs, they have a fixed state. Like they're like, okay, we are only going to dedicate this much memory, or like they have a fixed size of the memory which stores all the information about your context. The benefit is that you can have 1,000,000 context length or 2,000,000 context length, and the size of that will remain same. So your speed will remain the same no matter how long text you've outputted or how much is your input length. And the memory will also not grow. But the drawback is also that since just the amount of memory is limited, it becomes really difficult for it to remember something which was long ago, which happened like really long ago. So yeah, they are faster, but at least in our experiments and like I think the papers that I read, I mean, there are papers which propose a new architecture and then they claim that, hey, we are really good at long context abilities and all that. But in the end, when you try to verify that, like you find that transformers are better. And that's why most of these actual big models are like hybrid. They have Mamba, but they also have like a few layers of full attention.
Oh, gotcha.
Yeah. So yeah, that's essentially what these models are. They have like a fixed state, which like that's the state of the machine, which summarizes the context that it has seen so far.
Okay, got it. So then, even with you said the larger ones, the idea is that you still, from a Mamba architecture, they still have a full attention. So sort of like how we talked about, you might miss it a couple times because from a long context, that information isn't there. But because 4 or 5 layers later, there is a full attention layer, you can always go back to that. It presumably would slow things down a little bit because you've got the full attention, but then you would actually still have a hit. You wouldn't have a miss, basically.
Yeah. I mean, although like pure Mamba just refers to all the layers being Mamba layers, no attention layers. But I think there are some models, I forgot the names because they're named really similarly, like Mamba, Jamba, Samba,
Oh,
and then even Zamba.
Jamba, yeah.
Yeah.
Gotcha.
I
Samba,
think
right, that one. Yeah.
Samba or Jamba, one of them has like a hybrid architecture where you have Mamba layers and then full attention layers.
Gotcha. All right, that's really cool.
Yeah.
And so it seems kind of like the crux of the issue is just how much context we should be passing into an LLM. So like taking some stats from one of your other blog posts, like the Great Gatsby, I think had 72,000, roughly 72,000 tokens. That's most of the modern models have a long enough context window to pass that in. Whether or not you should pass that in is a separate question.
Yeah.
But I'm just curious, do you think that this kind of like continual expansion of the context window is the way to go? Like, are we going to start seeing much larger context windows, or is it kind of diminishing returns of it's not actually able to be as effectively leveraged? We should instead focus on ways of reducing the amount of context that's passed in.
Yeah, so that's a really interesting question because that's a very active area of research, like outside and within Databricks as well. So one thing is, let's just use the use case of RAG, right? Retrieval Augmented Generation, where you have where you want to ask, let's say, a model a query. So what you do is you retrieve the relevant documents from your database and then feed all those documents into your LLM and then ask it the question. And based on those documents, the LLM outputs some answer. Here, your quality could be really improved if you have a really good retriever. Like the quality of those documents which you retrieved, if they are really, really relevant to the query, the output will be really good. And the other direction you could go is you could have a bad retriever, but then your LLM has like a million contexts, and so you're just feeding maybe even your entire data set into your context, and then your LLM just figures out. I would much rather have the former case where you have a really good retriever so that your LLM's context window doesn't need to be that large. Because in the end, LLMs are expensive to run, and also not just expensive, like mainly slow. So if also intrinsically, like your quality does degrade after some length. So yeah, I mean, figuring out what the trade-off is and like building better retrievers, and then like I think that would be a better direction. I mean, obviously, you should continuously work on trying to improve the long context abilities of your model. But from a practical perspective, also exploring that other direction is important. Where like building a system around these LLMs and ensuring that the system itself is good enough, and then like not all the weight is like LLM doesn't bear all the weight. Like the system also bears some of the weight.
And that makes a lot of sense. It's not just the quality, it's also the cost and the latency to consider as well. Well, we just want to say thank you so much for joining us today, Shashank, enlightening us all on mixed attention and the benefits of combining both sliding window attention with traditional attention for kind of the optimal performance and quality trade-offs, and just overall discussion on direction of research and LLM. So thank you so much for joining us today on Data Brew.
Thank you for inviting me. It was a pleasure.